everybody, good morning. Myself, Dr. Shubhankar Sen, an Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the second lecture of Module 8 of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall introduce the concept of Peclet number. Peclet number is a non-dimensional number that is very much important in conjunction with the convection, diffusion, transport, mass transport, or the momentum transport. It is named after the French physicist Jean-Claude Peclet. Subsequently, we shall illustrate the convection diffusion matrices for one-dimensional bar elements. We shall show cases for two-noded and three-noded bar elements. First, we introduce the concept of Peclet number. The Peclet number, denoted by the symbol Pe, is named after French physicist Jean-Claude Peclet. The Peclet number, it is represented as the ratio of strength of convection transport to the strength of the diffusion transport. Peclet number represents the ratio of strength of convection transport to that of transport via the diffusion mode. We have already discussed the generic transport equation in the early lectures of this course. So, the generic transport equation, the generic transport equation for a transported quantity phi is given by the following transport equation written in coordinate free or vector form for phi equals to a function of both space and time. The equation is given by del t of rho phi plus divergence of rho v bar phi equals to divergence of gamma grad phi plus s phi. So this is the generalized equation. The first term, it represents the unsteady term. The second term represents the convection or advection term. The third term, or the first term in the right hand side, it represents the diffusion term. And the last term represents the source term. This particular presentation, where the convection and diffusion fluxes are considered, is known as the strong conservative form of the governing equation. This is the strong conservative form of the governing continuum equation. This equation has already been discussed. Now, here rho is the fluid density and gamma is the diffusion coefficient. For momentum transport, gamma is the dynamic viscosity mu. For energy transport, our gamma is the thermal conductivity K. Now, the Peclet number is represented as rho UL by gamma, where capital U reference velocity in the flow and capital L, this is the reference length scale. So this representation of Peclet number, this is for the global Peclet number. The global Peclet number, which is a constant, which is not a function of the coordinates. So not a function of coordinates. For momentum transport, PE equals to rho UL by mu equals to UL by mu by rho. So this is UL by nu, and nu is the kinematic viscosity of the fluid. For energy transport, PE equals to rho Cp UL by K equals to UL by K by rho Cp equals to UL by alpha. So here nu is kinematic viscosity, alpha is thermal diffusivity. It should be noted that the unit of the transport coefficients nu and alpha are same. It is meter square per second. The Peclet number in thermofluids is expressed as PE equals to RE into PR, where RE is the Reynolds number, equals to QL by nu, and PR is the Prandtl number. Equals to nu by alpha. Now we can define the Peclet number at the element level or the cell level, and we denote it as the cell Peclet number. If Peclet number is much greater than 1, we say that the flow is convection or advection dominated, and the transport by diffusion mode is very weak. In most of the problems of engineering relevance, the Peclet number is very large. Now we define the cell Peclet number. The cell or element Peclet number denoted as PEX is defined as Pex equals to C into delta x by 2 nu, where C is the convective speed and delta x equals to mesh size. In context of finite difference or finite volume methods, the cell Peclet number is denoted as Pex equals to C delta x by nu. But in case of finite element formulation, we have the coefficient 2 with nu. For stable GFEM solutions of flow problems under the convection diffusion regimes, the absolute value of cell Peclet number, it must be less than equals to 1 or minus 1 less than equals to Pex less than equals to 2. In context of finite difference and finite volume method, this range is given as cell Peclet number absolute value less than equals to 2 or minus 2 less than equals to cell Peclet number less than equals to 2. The factor 2, this is based on the definition of Peclet number by using finite difference, finite volume methods and the finite element method. Here, certainly, this is 1, and I also mention here that the Peclet number is a non-dimensional number. Now, we shall show the convection and diffusion matrices for the bar elements. The convection, diffusion equation in strong form is expressed as del u del t plus C del u del x equals to nu del 2u del x2 plus Sx. So this equation we have already dealt with in the first lecture of this module. So we have already got the expressions for the convection matrix, diffusion matrix as well as the mass matrices. So the element level convection matrix is defined as Cij equals to Ce equals to C into integration over omega e psi ie del psi je del x d omega e. The element level diffusion matrix is defined as Dije equals to De equals to nu into integration over omega e del psi ie del x del psi je del x d omega e, and the element level mass matrix is denoted as Mij equals to Me equals to integration over omega e psi ie psi je d omega e. Now let us go for the two-noded bar element first. Consider a two-noded or linear bar element. So this is the two-noded or linear bar element E. Local nodes are 1 and 2. Its mesh size is delta x. So for this element, we have already calculated the convection matrix in the 7th module. The convection matrix for this element is obtained as CE equals to minus C by 2, C by 2, minus C by 2, C by 2. This is a 2 by 2 matrix. The diffusion matrix is expressed as Dije equals to De equals to nu by delta x minus nu by delta x minus nu by delta x and nu by delta x. For two-noded bar element, we have already discretized the Laplacian operator at the early stages of this course. So that Laplacian operator was discretized in conjunction with heat conduction problem, where the diffusion coefficient was thermal conductivity. Here the diffusion coefficient is nu, so we have replaced k by nu in this expression and we have got the element level matrix equation system. Now we want to represent the diffusion matrix in terms of the dimensionless Peclet number. The Peclet number at the local level is a dimensionless number, and we express the diffusion matrix in terms of the cell Peclet number. Since Pex equals to C delta x by 2 nu, we may write nu equals to C delta x by 2 into Pex. The diffusion matrix is therefore expressed as dE equals to nu by delta x minus nu by delta x minus nu by delta x, nu by delta x. This comes as dE equals to nu by delta x. So this is C delta x by 2 Pex into 1 by delta x minus C delta x by 2 Pex into 1 by delta x minus C delta x by 2 Pex into 1 by delta x, and finally C delta x by 2 Pex into 1 by delta x. From each entry, the mesh size, it gets cancelled out. So we get here C by 2 Pex minus C by 2 Pex in the first or last term. Then we get again here as minus C by 2 Pex, and finally the d22e term is C by 2 Pex. So we have obtained the diffusion matrix and the convection matrix for the two-noded bar elements. The combined convection, diffusion, element level 2 by 2 matrix for the two-noded bar element is given by CE plus DE equals to minus C by 2, C by 2, minus C by 2, C by 2, plus C by 2 PEX minus C by 2 PEX minus C by 2 PEX, C by 2 PEX. If we see these two matrices, both of these matrices, they are linearly dependent. Both CE and DE are linearly dependent. CE is asymmetric, but DE is symmetric. Therefore, CE plus DE must be asymmetric. So, the combined matrix at the element level due to convection and diffusion effects may be expressed as C by 2 into minus 1 plus 1 by PEX. Here it is 1 minus 1 by PEX. Here it is minus 1 minus 1 by PEX, and here the last term is 1 plus 1 by PEX. So we have got the element level convection diffusion matrix in terms of the non-dimensional number, the controlling parameter, which is the cell Peclet number. From the condition of diagonal dominance for stable solutions, it can be proved from this element level matrix that the absolute value of the cell Peclet number must be bounded by 1. The diagonal dominance requirement of the element level and global convection diffusion matrix will lead to the absolute value of Peclet number must be less than equals to 1 condition violation of this restriction will lead to oscillatory non-physical solutions. The mass matrix for the linear bar element is expressed as ME equals to delta X by 6 into 2, 1, 1, 2. So here we rewrite the combined convection diffusion matrix once more. So here we have CE plus DE equals to C by 2. C is the convective speed. Here we had minus 1 plus 1 by PEX. Then we had 1 minus 1 by PEX. Here we had minus 1 minus 1 by PEX, and finally we had 1 plus 1 by PEX. Here C is the convective speed or velocity. Now we present the same quantities for the three-noded or quadratic bar elements. The convection, diffusion and mass matrices for the three-noded or quadratic bar elements. So let us draw a quadratic bar element. This is element E. So delta x is the mesh size and local nodes are 1, 2 and 3. These matrices have already been calculated in module 7 or even before for the diffusion portion, and in module 7 we have shown the convection matrices. The convection matrix is expressed as CE equals to minus C by 2, 2C by 3, minus C by 6, minus 2C by 3, 0, 2C by 3, C by 6, minus 2C by 3, and finally we have C by 2. This is the convection matrix of the size 3 by 3. So now similarly we can have the diffusion matrix. The diffusion matrix is given by DE equals to nu into 7 by 3 delta x minus 8 by 3 delta x, 1 by 3 delta x, minus 8 by 3 delta x, 16 by 3 delta x, minus 8 by 3 delta x, 1 by 3 delta x, minus 8 by 3 delta x, and finally 7 by 3 delta x. Putting nu equals to C delta x by 2 PEX here, we obtain DE equals to C delta x by 2 PEX into 7 by 3 delta x minus 8 by 3 delta x, 1 by 3 delta x minus 8 by 3 delta x, 16 by 3 delta x minus 8 by 3 delta x, 1 by 3 delta x minus 8 by 3 delta x, and 7 by 3 delta x. So removing delta x from all these terms, we get the final form of the diffusion matrix, so which can be written as 7C by 6 PEX as the first term. So this is 7C by 6 PEX. The next term is minus 8C by 6 PEX. The last term in the first row, this is C by 6 PEX. In the second row, we get minus 8c by 6Pex. The D22E term, it is 16c by 6Pex, 16c by 6Pex. The next term is minus 8c by 6Pex. In the third row, we have c by 6Pex. Next we have minus 8c by 6Pex, and finally we have 7c by 6Pex. 7c by 6Pex. So here we can combine the convection matrix and the diffusion matrix for the quadratic bar element. The combined convection diffusion matrix for the quadratic bar element is given by CE plus DE. So our CE, it was minus C by 2, 2C by 3, minus C by 6, minus 2C by 3, 0, 2C by 3, C by 6, minus 2C by 3, and C by 2. This is the convection portion. The diffusion portion which we got here, this is 7C by 6Pex minus 8C by 6Pex, C by 6Pex minus 8C by 6Pex, 16C by 6Pex minus 8C by 6Pex. In the last row we have C by 6Pex. Then we have minus 8C by 6Pex, and finally we have 7C by 6Pex. So we can combine these two expressions and we get the final form. So the first portion is the convection matrix CE, the second portion is the diffusion matrix DE. We have already mentioned that the convection matrix is asymmetric, and this is leading to skew symmetry when we assemble the convection matrix, and diffusion matrix, this is a symmetric matrix. So overall, when we combine them, we get an asymmetric matrix. So CE plus DE is a linearly dependent asymmetric matrix. CE is asymmetric. It leads to skew symmetry. We already saw it for the wave equation, and the DE is symmetric. So by combining these two expressions, we can take the convection velocity outside and then we can get a simplified form. So CE plus DE, it can be expressed as C into minus half plus 7 by 6 Pex, this is the first term. Then we have 2 by 3 minus 8 by 6 Pex minus 8 by 6 PEX. In the third we have minus 1/6 plus 1 by 6 PEX plus 1 by 6 PEX. In the second row we have minus 2/3 minus 8 by 6 PEX. Then in the 2 to E term we have 16 by 6 PEX, no convection contribution, 6 PEX. In the third term we had 2 by 3 plus, it will be minus 8 by 6 PEX minus 8 by 6 PEX. In the last row we have 1 by 6 plus 1 by 6 PEX. Next we have minus 2 by 3 minus 8 by 6 PEX, and finally we have half plus 7 by 6 PEX, 7 by 6 PEX. So this is the combined convection diffusion matrix for 3-noded or quadratic bar elements. We are left with the mass matrix for the convection diffusion problem using the quadratic bar element. The mass matrix for the quadratic bar element is given as ME equals to delta X by 30 into 4 to minus 1 to 16 to minus 1 to 4. The quadratic mass matrix we have already calculated in the previous week. Therefore, for the 2-noded and 3-noded bar elements, we have shown the structure of the convection diffusion matrices contributed by the convection term, contributed by the diffusion term, and we have also presented here the already calculated consistent mass matrix. So this is the consistent mass matrix. This is symmetric, positive definite, and certainly diagonal dominant. We conclude today's class here. We have interpreted the global Peclet number PE and element or cell Peclet number PEX in finite difference or finite volume context. PEX equals to C into delta X by nu, whereas in FEM context PEX equals to C delta X by 2 nu. So this difference in the definition, it also leads to the difference in the stability criterion for the solution. The stability criterion of PEX using central difference under FDM or FVM is given as absolute value of local Peclet number less than equals to 2 or minus 2 less than equals to cell Peclet number less than equals to 2. In contrast, for Galerkin finite element method, the corresponding cell Peclet number limit is expressed as absolute value of Pex is less than equals to 1 or minus 1 less than equals to Pex less than equals to 1. Subsequently, we have summarized the convection, diffusion and consistent mass matrices for the linear and quadratic bar elements. In each case, the convection matrix is asymmetric, whereas the diffusion and consistent mass matrices are symmetric. For today's class, I suggest the following books authored by Professor T.J.R. Hughes, Professors Donia and Huerta, and the S.V. Patankar's CFD book, particularly for discussions on the cell Peclet number or the basic definition of Peclet number. Students must go through the textbook by Professor Patankar. Thank you very much for attending this lecture.